just tell them like briefly, and then how you develop the model, which model you are showing. Yeah, so make some initial explanation.
Yeah.
Yeah.
Hi everyone. Am I audible now? Can
Yes.
you hear me?
Yes.
Yep. Thank you. So, if you've gone through some literature review on this topic, especially dynamic electrical equivalent modeling of proton exchange membrane fuel cell, this is the most demanded fuel cell. As you know, I think there are several types of fuel cell like alkaline fuel cell, proton exchange membrane fuel cell, and solid oxide fuel cell. But if we are focusing on renewable based power systems, then PEM, that means proton exchange membrane, is the best candidate because it can adjust its output current profile very quickly as compared to other candidates like alkaline and solid oxide. So that is why PEM, proton exchange membrane, is very suitable for especially for renewables, because for renewable based power generation systems, as we know, solar and wind, most of the uh, most of the times they are changing in nature because of their dependency on climatic change. So that is why we are focusing today's my demonstrations focus more on proton exchange membrane fuel cell. So as we gone through some literature review, we see there are a lot of models available in the literature. Some are thermal models, some are chemical models, some are thermochemical model. So as a electrical engineering perspectives, we basically need electrical equivalent modeling, as we have resistor, capacitor, inductor. In same cases, we need a model circuit for electrical equivalent circuit for proton exchange membrane fuel cells. So this topic actually cover this. I think Professor Jangir already describes its different kinds and different mathematical equations used to model for this electrical equivalent model. So I am just going through very quickly to start the main part of this sections. That means the equations, chemical equations used to related to the fuel cell is given here. Here we can see. So here there are entropy. This is the part of entropy, and this is the Gibbs free equations in terms of mole. So we can, from these equations, we can write Gibbs free equations in this way. In equation 2 you see, then then because fuel cell is a electrochemical devices, it contains anode and cathode. These are commonly said electroplates. So the movement of electron from anode to cathode, it requires some energy to energize the electron through the outside, through the conductor of the outside, that means through the other circuits. So this voltage can be defined by these equations. Here we can see the reversible voltage. The reversible voltage highly dependent on the pressures of hydrogens, pressures of oxygens, and the pressures of water. So we can rewrite these first equations in terms of entropy and the energy release required for the chemical reactions. In the second, in the below one, here we can see. And then there are some others voltage drops in the fuel cells. These are called activation over potential voltage drop, ohmic voltage drop, and concentrate voltage drop, or mass transport over potential drops. So the cell voltage across the fuel cell can be defined by these equations. If there are a lot of cells connected in either series or parallel, then this voltage of this combined system can be represented by this one. So now we are going towards activations over potentials. So as I already said, a fractions of the supplied voltage is dropped by the process of moving electrons between the electrodes, which is referred to activations over potentials. Here in these equations we can see activations of our potentials basically split into two sections. One is for anodic activations of our potential, another one is cathodic. So here we can see these two part, anodic and cathodic here. So in broadly we can write these equations this way. Here we can see this way. If we combine this both anodic and cathodic, then we can generalizedly can write this one. So here is that once. So if we reverse the relationship, it is the relationship between activations of our potential to the current passing from the from the fuel cell to the external circuits. So we can just reverse the relationship like this way. Here two new parameter, here we can see this is alpha A and alpha C. This is the standard current coefficients for anode, and this is the cathode. So these equations actually we need for modeling. Later we can see. Then the next one is concentration over potential, or we can say mass transportations over potentials. It is basically the results due to the fluctuations in concentrations of the reactants. So here the reactants are, one is hydrogen and another one is oxygens. So because of the fluctuations of hydrogen's pressure, temperatures, or any other dependent parameters, this over potential has been resulted, and it's basically happened in high current density region, not low or moderate current densities. That is why most of the literature they are ignored this term until 3 ampere per centimeter square. So this part can be defined here, the same as like activations of our potentials. Concentrations of our potentials can be defined by two sections, one is anodic and another one is cathodic. So here it is highly dependent on the reactants concentrations, as I said. So this is the nominal concentrations of one reactants, that means happened in anode, this is oxygens, and this is happened in cathode. So this is for hydrogen concentrations. This is the ratio between the measured concentrations and the nominal concentrations for the fuel cell. Similarly, combinedly we can write these two sections in one equations this way. So here the concentrations of oxygens and hydrogens can be written in broad sense here. So here we can see actually the concentrations of hydrogens or oxygens both are dependent on the current going through the external circuit from the fuel cells. So if we relate these two equations, we can say concentrations of our potentials depends on the current moving towards the external circuit from the electrolyzer. So if this current density until this range, that means 3 ampere per centimeter square, then we can use these equations, and after that we can ignore this value. So here we can combinedly in short form we can write these equations for the concentrations of our potentials. So the most important things for electrical circuit designing, this is the ohmic of our potentials. So this is the ohmic of our potentials that can be caused due to the resistance of the membrane placed between anode and cathode and the resistance of the contact. So this is the two main parameters to results this ohmic over potential. So here we can see in equations. So this is the very basic law, Ohm's law. So this is voltage equal IR. So this is the total ohmic voltage drop for across a single cell. So we can write this total resistance quantity into two parts. One is membranic resistive drop, another one is contact resistive drop. So membrane resistive drop is as we know, the name of this fuel cell is proton PEM, that means proton exchange membrane. So we basically put any type of proton exchange membrane in between anode and cathode. So this highly depends on the conductivity of this membrane. So here we can see it is basically depend on the membrane type. It is not fixed. So this is the dielectric constant of this membrane. So this conductivity basically based on the membrane, what type of membrane we use for design that. So and contact resistance is two types. One is the anodic contact. So here we can see the contact resistance. So it happens for both anode and cathode. This is the equivalent resistance circuits for the contact resistance. So it has some others parameter here we can see. So we don't need this detail for electrical equivalent modelings. So now how we can calculate the efficiency of a fuel cell? So for calculating the efficiency of a fuel cell, we first need to know for supplying a required amount of current, what would be the supply of hydrogen in the input side of the fuel cell. So it is that equations, that means this is the this is mole per this is the volume of the hydrogen that need for supplying a specific load. So this is the volume per mole. So this is the very basic equations taken from the chemistry. So here R is the universal gas constant, T is the ambient temperature, as you know. So from here we can just reduce we can just represent these equations in terms of time, that means milliliter per minute. So here we can see we can use these equations, then we can rewrite these equations in terms of this parameter, the parameter we have here. So just replace this one. So then we have these equations. So here also we can see the required number of fuel, it is called flow rate. Simply we can say this left hand parameter, left hand variable, simply we can say flow rate. So flow rate depends on the current. Other parts all are constant here except the current. So if we need more current, definitely we need to provide more flow rate in the input side. If we need, so if the current required is fluctuating in nature, then definitely based on this we need to readjusted this flow rate. So here so this is the power supplied by the fuel cell. Here we can see it is based on the flow rate. So finally we can get the final equations. This is that one, that means the current supplying by the fuel cell and multiplied by reversible voltage. So this is the power. So then efficiency we can get, it is the ratio between nominal case and measured case. So finally we can find these equations. So from these equations, if we incorporate all the things, all three types of voltage drop as I mentioned here, all types of voltage drop, reversible voltage, activations over voltage, ohmic voltage and concentrations over voltage. So then we have a diagram figure like this way. Here we can see this is the mathematical model based electrical equivalent circuit of the proton exchange membrane electrolyzer. So here we can see, so this ohmic part actually represents the ohmic potential drops, these ones. So and here we can see there is a current dependent two parameters. One is for activation voltage over voltage and another one is for concentration voltage drop here. So another thing later we can see, when we can see the VI characteristics of this fuel cell, actually when we have a sudden change in the external current profile, voltage change doesn't change instantly. It needs some times to follow the external current profile change, because there is a time requirement to pass electron from one electrode to another electrode that cannot be reflected in the conductor, outside conductor. That means the conductor required to complete the circuit. This delay actually we can represent it by a first order time delay. So here we can see the transfer functions. Actually this voltage, this quick change current reflections take some times. This can be defined by this first order transfer functions. This is tau d. So tau equal the equivalent time required to pass electron from one electrode to another electrode through the membrane. So if we see the pi and Vi characteristics curve of a proton exchange membrane fuel cell, here we can see very, after zero you see there is one range, one vertical range. This is actually the very low current density regions, and this voltage actually, this regions actually represents activations voltage drop, because this is the very minimum voltage you have to supply between electrodes to energize electron to transfer one electrode to another electrode, let I say anode to cathode. So until supplying this voltage, it cannot be start supplying current to the external circuit or power to the external circuit. So that is why this voltage reflects in the very low current density. So you see this is also non-linear. The nature of this curve is non-linear. Here we can see if we make little bit zoom, you see this is non-linear curve. Because if we see the equations, final equations here activation voltage drop, you see it is not a linear relation, it is a non-linear relations. So that is why this curve also shows non-linearity here. And after that you see until this vertical range, here we see another vertical, this region is a linear region, because this region occurs due to the ohmic voltage drop. And according to the Ohm's law, it is a ohmic voltage drop. Definitely it depends only V equal IR, only the resistive elements. So it is a linear region, you see. And from this curve we can say there is another regions after this vertical line, there is another regions. This is a high current density regions, and this regions there is another voltage drop. This is mass transport over potential drops or concentration drops. Here we can see. So this is also non-linear because of their mathematical nature. From this mathematical nature we can see. So this line actually, this curve is Vi characteristics curve. And another curve, if we draw here, it is based on current versus power curve. So this is called Pi characteristics curve. So it's look like that. If we multiply each points, P equal Vi. So if we multiply each points current into current and voltage, then we can easily get this power characteristics curve. The intersections between Vi and Pi characteristics curve, here we can see this is the intersections point. Actually this point defines the optimal operating point of this fuel cell. We always try to operate this fuel cell at the intersections point, or it is called nominal operating point. And this one, the red, you see the red dot, this is the maximum power operating point. That means at this point we have very extreme limit of the ohmic region. You see, this is, it actually happens the extreme limit of the ohmic voltage drop regions. And after that we have non-linear, so it suddenly reduce the power. You see here, because of the non-linear characteristics happens due to the concentrations voltage drop. So here you see in this equivalent circuit diagram we use a first order transfer functions. So this is actually explained here. From the first order circuit we have this one, this is the basic equations of a first order RC circuit. If there is RC circuit, so this one, so this is the first order time delay. So as we know, this is time constant in another term we can say. So time constant equal RC. So R actually is the equivalent resistance of ohmic and anodic and cathodic voltage drop. This is the equivalent resistance, and CD is the equivalent delay to transfer electron from one electrode to another electrode. So this is actually the basics, mathematics, and the modelings of a proton exchange membrane electrolyzer, fuel
So
cell.
Biplab, maybe now we
So
go for like MATLAB. Can you please?
yeah. Now I'm going to a very simple circuits. So I previously modified a circuits for you. So this is
So
the fuel cell.
yeah, Biplab, just a minute. So have you given that circuit to everyone?
This one.
Okay, I mean, if they want to build it, it might be. Yeah, I mean, Biplab, you just
Okay.
you start
I-
like
I-
the existing one from MATLAB.
Yes, sir. I actually prepare 3 tasks for the attendee. So after just describing this model inside, so I will give them this task. Is
Okay,
it
so
okay?
maybe you just open the existing model from there.
Yeah.
So and then if they want to do it, how they gonna find the model? You can show them because
So we can find, yep. So if this is the Simulink interface of MATLAB. So if you double click right on your mouse, double click the cursor, so then there is a new pop-up, search block will come. You just write here fuel cell. So we need to use this one because we are going to model electrical circuits. So that is why we need electrical specialized power systems. So just click this one. So you see the similar block comes
so
here.
Biplab, I mean, just wait whether just to see like, has everyone got this block, MATLAB? Anyone have problem? Okay, no, then you keep continue. Yes, like after
Okay.
like this model maybe just explain little bit inside what is there and then go from there.
Yeah, if you double click the block, this fuel cell stack block, double click, right cursor. So here we can see actually you can use your own developed model, or you can use built-in model provided by MATLAB. So preset model. So here we can see there are a lot of, so if you choose this one, you can then provide the details of your own developed model in the remaining below blocks, below field. If you there are other some built-in stacks. So you see this is proton exchange membrane fuel cell. This is 1.26 kilowatt, and it can provide 24 volt DC at the output terminal for nominal operations. Another one is, this is also PM. It is 6 kilowatt 45 VDC. So in such way you can either use built-in fuel cell or you can use your own defined fuel cell. For example, here for this one I am using 6 kilowatt 45 VDC fuel cell stack, and this is PM. So after that, so these parameter sections you can define here. So you see voltage at open circuits and 1 ampere. So you can define this voltage at 0 ampere and 1 ampere. If you click here, the VI characteristics curve here. So you see the VI characteristics curve, the upper one, and the lower one is the power characteristics curve. So if you combine these two so this is the intersections point. So it is called the nominal operating point. So what would be the value at 1 ampere? You can define. What would be the, in such way you can define other remaining network parameters. So stack parameters like this way. So what would be the nominal current, what would be the nominal voltage, you can define here. So we can see here the nominal current is 133 and nominal voltage is 3.45. If you click the VI characteristics curve, we can see the same value here. So you see 133 is the ampere and 3.45 is the voltage for this. Sorry, 133.3 is the current and 45 is the voltage. So in such way the nominal power this much 6 kilowatt. In such way you can define the characteristics curve of your own defined. So if you choose any one pre-built, you see most of these things are hidden now, inactive. You can't insert this value because this is built in. So after then another field, this is called signal variations. So what type of fuel consumptions you have to input in your fuel cell stack, you can provide it by using external input probe. Like if you click here one, so there is an input probe you can define here the fuel consumption percentage. Like
so what is here, like, I mean, there are some internal, but if someone wants to give their own input, they can do it, right?
Yeah. So if you want to provide specific value from your design perspective, you can put. Otherwise, if you doesn't select any input probe, then all things actually the built-in functions thinks all the input are sufficient. They provide current and voltage based on these things. They are thinking that all things are provided sufficient. There is no deficiency. And if you want to make it more realistic, like there might have some deficiency, there is some surplus this value, then you can provide this specific value. So after then, this is the fuel cell dynamics. So actually if you want to fuel cell dynamics, actually this is the time. The time, as I said, first order time delay, you can define this time from here. So these are the parameters input things. So just I'm going through a little bit quicker with this help. So this is that circuit, but the available MATLAB built-in circuit, they are ignoring concentrations over voltage. Here we can see this is the equivalent of ohmic voltage, this resistance part, and there is a current dependent one parameter only, you see. So this is the equations for activation voltage drop only. There is no another parallel connections in this presentations. You see there are two sections parallelly connected. So one is for activation voltage drop, another one is for concentration voltage drop. But MATLAB built-in one, there is no concentration voltage drop. It is designed for low current density applications. So the same things here we can see, this is the activation voltage drop region, this is the ohmic regions, and this is the concentration voltage drop regions. The equations I showed, they are explaining this all equations here. And here we can see if we want to input this parameter, we can easily input this parameter by selecting from the signal sections. So this is the equations for utilization factor. For example, for battery, we know the term SOC, state of charge. Basically, we are going to use battery for a manufacturer specified range, like 10% SOC to 90% SOC, or 50% SOC to 70% SOC. Same way, we have to define here fuel utilization factor. One is for hydrogen, another one is for oxygen. If you want, then for example, the wise practice for fuel cell operations, hydrogen utilization factor keeps between 80% to 90%. More specifically, it is 85%. So in such way, you can define this value from using these equations. So these are the equations how you can calculate pressures of each reactants by using the compositions of fuels. So this is the equations here we can already describe. Another important thing we need, this is at the end we can see here this is the fuel flow rate. Fuel flow rate. So actually, if we need a specific amount of current need to be supplied across a load, so based on this requirement, we need to supply the required flow rate either for hydrogen or air, that means oxygens. So we can define these things using these equations. So using these equations, so these are the basics about the built-in fuel cell stack provided by the MATLAB.
So
So these are
Biplav,
the basics.
they just want like 10 minutes break. So meantime you can have a tea or something like that, and then you can give like showing how to do that simulation. Okay.
Okay, yeah.
So
Thank you, sir.
yeah,
Okay.
so just like 10 minutes. So you can start after 10.